Good afternoon, everyone. My name is Francesco Villasmunta. I developed Plotivy during the final phase of my PhD, and I'm very excited to share it with you today. Plotivy is meant to transform your research data into reproducible, publication-ready data visualizations. Let me start with a question. So, how do we move from raw experimental data, such as the one represented here, whatever shapes they come in, to a visualization that is beautiful, honest, and publishable? And how long and how difficult do you think it will be to do it with the standard tools like Excel, OriginPro, MATLAB, or Python? That's the core question that Plotivy was built to answer, how to generate such charts in an effective way. So for this, three things needs to happen. The analysis has to be reproducible, has to be ethical and effective at communicate a message following the best practices for data visualization, and needs to meet journal requirements. Let's go step by step. When you read that the paper says that, for example, a Savitzky-Golay filter was applied for smoothing, you don't know, for example, what were the parameters most of the time. You don't know the window length, the polynomial order, you don't know if the parameters were used consistently across different samples, and the problem here is that if you cannot see the math, you can't verify the science. It's a reproducibility problem. And with tools like Excel, OriginPro, the process that goes from raw data to a published figure is almost never documented well enough. And this problem affects even the original author when opens the folder 6 months later and has to work again on those figures. On this reproducibility scale, somehow MATLAB is in the middle, but the problem with it is that it's expensive and proprietary software. And Python, at the other end, is free, is accessible to everyone, and is used by many researchers across the world, and solves this problem because the code itself is the documentation. And every parameter, every transformation is written there and runs the same way every time. Now, reproducibility is one thing, but even with a perfectly reproducible figure, we need to communicate the right thing effectively. And I want to show you an example. Here you see two charts. They represent exactly the same data, but can you spot the dramatic and deceiving difference here? On the left chart, it was used a non-zero baseline, so you see that the values start from 34%. And on the right side, it was used a zero baseline. So where this difference of only 4.6% is correctly represented. And that's a thing that if you didn't notice already, happens so many times, and it's a bad practice in data visualization. And this and many other practices need to be applied, and Plotivy applied them automatically. Now is another point here. There are several types of charts that almost no one uses. Not because they are bad or something like that, but because most of people don't know that they exist. And there was a survey where you can see how many charts were known by the participants and how many were actually used by them. And we see that basically, for example, a violin plot, which is very good to represent distributions, since it doesn't hide like a box plot, for example, in categorical data, or for each category of data, doesn't hide the distribution behind it. And the violin plot is almost unknown by many, let's say, plot makers, such as researchers and so on. And Plotivy, on one hand, also helps make this kind of charts more accessible. Now, another point, journal requirements. So, this point is technical, but when you're going to submit a paper, for example, matters a lot. It's very important. Here is a figure that on the left looks perfect on, let's say, in this size on your screen and so on. But the moment this figure goes in a published paper, depending on the format this figure was generated and exported, will either look like this or like this. And this is a tricky point because, for example, you zoom a lot in a PDF to better look at the graphs, and then something like this happens. And Plotivy helps you extremely easy to export data in vector format, so that scaling doesn't matter anymore. And Otherwise, every journal has also a certain style requirements, some review requirements or requests on the figures, and Plotivy applies journal styles for several editors like Nature, IEEE, and so forth and so on, automatically when you create a figure. You can select it. So, what is Plotivy? The question that you're probably asking yourself and partially answered. Plotivy is a web application, first of all, so you don't need to download and install anything, that supports your complete research workflow. It starts from organizing and planning your experiments to collecting your data, generating a publication-ready visualization, and documenting your results in a way that stays reproducible for years. Because once you have the code, the data, you can basically regenerate each figure for eternity, basically. Let me show you now how these specific tools work. For example, we have in Plotivy, if you go to the header and you choose Research Toolkit, a folder structure generator. You start a new project, you want to keep everything organized, you let's say personalize, customize your folder structure here. You see that some principles are applied, such as raw data go in a folder and should never be touched, and the new processed raw data go in another folder, and so forth and so on. But the beautiful thing is that then you download a script, you execute it in your PC, and you have created for you exactly this folder structures for your new project. Second point is design of experiments. I spent years doing plasma etching experiments during my PhD, and getting the experimental design right, so choosing which variable to vary at which level and in which order, determines the quality of your statistical conclusion. And Plotivy has a factorial design of experiment tool that, after following several steps, produces a ready-to-fill experimental table, which is statistically sound, like the one you see here with the runs and your levels and replication, randomization applied, and where you just go to the lab, input these parameters, and then you produce your sample, and then, for example, you go to characterize it, and you fill some other variable, output variable from the characterization, and then you take these results and you visualize them. So this is the most important part of Plotivy, the generation of Python code by AI. You describe the figure of the analysis that you need in plain language, and Plotivy writes the Python code for you, which is fully commented so that you can understand it, modify it, run it again. You can execute it there, right in the browser, and you see the figure and you see the code that produced. So now the question is, if Python is so good, why doesn't everyone just use it? The answer is, I guess, friction. Python requires setting up a local environment, then you need to learn the syntax to write code. Every new type of figure means that you need to write a new formatting code from scratch, and if you want to explore a new visualization idea, you have to develop a new code for it, and you cannot reuse the same template that you developed at the beginning to plot always the same line chart, for example. And this makes iteration slow, and debugging is frustrating, and researchers should spend more time on science and not debugging but validating the written code, and this is fundamental. The responsibility of the person who is using AI generated code is to validate what has been produced. But once you find that everything is fine, your code is ready to for publication in a point is that Plotivy removes this friction. You don't need to install anything, you don't need a local Python environment, you don't need any license. Plotivy is free, and you can just open any browser, go there, type plotivy.app, and start visualizing your data. Okay, now let me show you all of this in action. Let's do a demo. Okay, here we go with the demo. This is the homepage of Plotivy. From the top, you can access several resources, the different research tools, and then we have a gallery with different chart types. As you can see, Python or Plotivy can generate more than 100 types of different charts, and you can open this and find all the characteristics of a chart and play with them. But now let's move to the data visualization. So in this page, you have at the top several examples that you can run just to see how the app works and play a bit with it. Or you can start with your own data by uploading a file or pasting them. You can plot a formula from natural language, from LaTeX, or from a screenshot. or you can start with your own existing Python code. Now we will upload a file and start working on it. So this is a spectrometric file. We have here wavelengths and here intensity. It looks good, so we can import it directly. And we can modify the column names to wavelength in nanometers and to intensity in arbitrary units. Okay, now we can have a preview of it. Here is represented as a scatter plot. You can see on the left the spectrometer was not measuring. Then we have, let's say, a reflection signature of the substrate, a silicon substrate, with the silicon dioxide mask over it. And here we can convert it to a line chart, and we see the fast oscillation. And actually we can zoom between 500 and 600 nanometers. And since this range looks good, we can filter our data. So we can transform them, wavelength greater than 500 nanometers and less than 600 nanometers. Okay, now as you can see, our filter has been applied, and we can start with an exploratory analysis. This means that Plotivy now will generate several types of different charts to help you find some insights. If otherwise you already know what you want to plot, you can use this input area to generate a visualization. Here you can select a certain style, journal style, and different types of intelligence, and you can write here your request. If you don't know, for example, what color scale to use, you have several examples here, which color palette, which type of chart you want to do, and so forth and so on. Now the exploratory data analysis is running. As you can see, we have several types of charts here, and we can just click on whichever we want. For example, this one. We can view many of them, and we can load it in the editor. So now the chart has been loaded in the code editor, and it can be modified. Let's start with modifying it. So let's ask to convert it to a line chart and to convert it and to detrend it and convert wavelength to wave number, which will be useful for the fast Fourier transform. Now the AI is modifying the code actually that generates this chart. And here we go. We have our detrended intensity versus wave number chart, which is homogeneously spaced without a chirp. And we can move to the next step, which is the conversion to fast Fourier transform. So make a fast Fourier transform and identify the peak, which corresponds to the depth of a through silicon via in micrometers measured by white light reflective interferometry. Okay, let's also plot this as a second chart below the existing one. Okay, of course everyone can use its own approach. If you already know, for example, which Python functions you want to use exactly to make your analysis, you can specify them, and this will be applied. Below you see the console output, which shows some values, and here we go. We have our chart with the original data, the fast Fourier transform with the measured TSV depth, and this is ready for publication, for conference, for poster, whatever you need it for, report. Most importantly, here you see the code with the changes, and you can modify this code. You should validate this code. You should read it, check that everything was in order, that everything is in order, that the mathematical functions are used correctly, that the data are processed correctly, and then you are ready to publish it. But you save time to write the code, to debug the code, and you just need to make sure that the code is right. Here on the left you find also the visualization history. So here we see the different steps. We can load them at any time back, and you can generate the caption by just pressing here, generate caption. And very importantly, you can generate a report. So here we can change the name, let's say TSV depth by white light reflecting interferometry, author Francesco, and we generate our report, which is here. It has the data summary, it has the prompt history, the final figure with the caption, the code, and other information. And this means that if you export this package all together, where you have your dataset, your figure, your Python code, and the analysis report, you can reproduce these figures in 10 years and still know exactly how it was done and talk about it with the reviewer and everything. You can also save it here and access it anytime, exactly as it was made. So here you see I have my folders with several examples, and I can access them at any time. So there is a lot here. I hope the demo was clear, and now let's go back to the presentation. Okay, I hope you enjoyed the demo. In summary, Plotivy was built to give every researcher access to the Python standard. Your figure becomes reproducible, your analysis becomes auditable, your publications are stronger, and your students, for example, learn real scientific computing by reading the code that generates the figure. You just open any browser and you're ready. If you have questions, you can reach me at plotivy.info@gmail.com. Plotivy is live at plotivy.app, and you can try it with your own data today. And I thank you very much for your attention. I hope this was useful, and I wish you an excellent rest of the event. Bye.